Number 4, they want us to draw a Lewis electron dot diagram for each of these molecules. Pretty straightforward, so let's get started. Let's see, I've drawn the sort of the structure of H2S over here. Each hydrogen donates 1 electron. Since there's 2 of them, that's 2. And then each sulfur donates 1, 2, 3, 4, 5, 6. So that's 6 plus the other 2 is 8 valence electrons for us to work with. And so I'm going to go around the outside. No, I'm not actually, because it's hydrogen. So we got to go back and erase those. Remember, nothing goes on hydrogen on the outside. So we've already used 4 in the bonds. We've done the outside, and then we're going to do 5, 6, 7, 8. And there we go. That's a perfectly good Lewis structure. Double check to make sure everything is happy. Hydrogen only needs the 2 in the bond. Sulfur needs 2, 4, 6, 8. It's set, and that hydrogen has its 2 in the bonds. We should always check that at the end. And then you know why we're here? Let's do B for the second for this one as well. There are 1, 2, 3, 4 electron domains coming off the sulfur, and so that means its rough shape is going to be tetrahedral. But of course, it's not really going to be tetrahedral. It's going to be tetrahedral where 2 of these little atoms are actually lone pairs. So I'm going to get rid of this and that. And I'm going to make those lone pairs with orbitals. And then it becomes pretty darn clear that what is left is bent. And so we will write bent. And they didn't ask us for bond angles, but it would definitely be slightly smaller than 109 degrees. All right, let's do the second one, SO2. SO4. 2 minus. And so we're going to draw it as S being in the middle, O, 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 O. And each oxygen contributes 6 valence electrons. The sulfur also contributes 6. So 6 times 5 is 30. But you got to remember we also have the 2 electrons from the charge. So we actually have 32 to work with. I'm going to write that down up here so I don't forget. Then we're going to go around the outside. You would be coloring these dots a little bit darker. And we've used 8 around each one. 8 times 4 is 32. And we're done. We could check and see how we're doing here. You notice that the oxygens all have 8. So does the sulfur, 2, 4, 6, 8. Now there will be some people who will say that you should share electrons because sulfur can do more than 8. Generally I'd recommend don't share unless you have to. Go just based on the octet rule. So we're going to stop there. And also because if you share more, it doesn't change the shape. So in part B, we just need to determine the name of it. So there's 1, 2, 3, 4 directions coming off. It's definitely going to be tetrahedral. And we could draw it out, but I think we're just going to label it tetrahedral. Probably will have very close to 109.5 degree bond angles. By the way, a little bonus information here. We're going to stop and think about something. If we were going to decide which one of these 2 molecules would dissolve in water, remember that polar molecules tend to dissolve in water. This one, being bent with dipoles that don't cancel out, would be polar. So we would expect it to dissolve in water reasonably well. Also, it has a lone pair of electrons which can hydrogen bond with water. So there are a lot of things that might cause us to think that will dissolve in water. This one you might say, well, if it's going to be tetrahedral, so it's going to be this shape, except for with 4 things coming off of it that are all the same, you might say, well, that's nonpolar. But here's an example where it doesn't matter because it's a charged compound, and so this would definitely dissolve in water because it's polar. All right, very good. Let's go do the last 2. All right, XeF2 is going to have, let's see, Xe contributes, where is it? Oh, it's right there. So it's going to be 8 electrons, 1, 2, 3, 4, 5, 6, 7, 8. And the fluorines are each going to contribute 7. 7 times 2 is 14. 14 plus 8 is 22. So I think we have 22 to work with. And then we go around the outside. we've used 16 electrons, then 17, 18, 19, 20, 21, 22. So this is one that definitely has an expanded octet. And so then if we're going to figure out its shape, it has 1, 2, 3, 4, 5 directions coming off of the center. It's going to be trigonal bipyramidal in shape. So that's the one with the head up there, the feet down there, and the Mercedes star around the belt. And you remember that it's these belt line ones that is where lone pairs go. So I have 3 lone pairs, and all 3 of these are going to be lone pairs, like that. So the shape that's left is clearly linear, and the bond angles are going to be 180 degrees. If we're thinking about whether it be polar or not, remember that this is fluorine, that's fluorine, this is Xe. Fluorine is definitely more electronegative, so if we drew the dipoles in, they would look like that, and they would cancel, so this would be a nonpolar molecule. And it definitely would have almost no solubility in water because it is not charged and it's nonpolar. And the last one, ICl4 minus, I is going to go in the middle, the Cl's are going to go around the outside, and then we got to count our valence electrons. Each chlorine is going to contribute 7. 7 times 4 is 28. And then the iodine is going to contribute 7 anyway. So actually 7 times 5 is 35. But you remember the 1 negative charge, so it's 36 total. Start around the outside. And we've used 8 times 4 is 32, then we go to the middle, 35, 33, 34, 35, 36. If we're going to figure out the Vesper shape, iodine has 1, 2, 3, 4, 5, 6 directions coming off of it. 4 bonds and 2 lone pairs. So that's going to be octahedral in its main shape. There's the little head, there's the feet, and then unlike the previous one, it's going to have sort of the X in the middle like that. And in this one, you remember the lone pairs are opposite to each other. You could put them anywhere. You could put them, say, there and there, or you could do top and bottom. It's up to you. So if I erase this one and this one, and you see that the lone pairs are actually going up and down, or sort of out towards us a little bit, but it doesn't matter. Either way, it turns out to be square planar, and the bond angles are going to be 90 degrees. Let's see, would it dissolve in water? Well, we might say if all of these are chlorines and they're perfectly offsetting each other, which they are in the actual molecular diagram, there would be no net dipole moment. But this was a charged compound, and being a charged compound, it's likely that it would dissolve in water.